Hi students, in my last video I completed non-ideal solutions as well as azeotropic mixture. In today's class, that is lecture number 12, I'll start with the colligative properties. Right, but before we'll going to see the colligative properties, in my last video while explaining ideal as well as non-ideal solutions graph on y-axis by mistakenly I took partial pressure instead of vapor pressure. Okay, please make it correct as vapor pressure. On y-axis it should be vapor pressure, on x-axis of course it is a mole fraction. And while explaining a vapor pressure term, I used vaporization instead of evaporation. That's it. Okay, right. Now we'll continue colligative properties. Colligative properties. Yeah. First we'll define what are colligative properties. Very simple. Colligative properties, nothing but the properties which depends on number of solute particles. I'll repeat. Colligative properties means the properties which depends on number of solute particles but not on their nature. It is a democracy property. In our democracy also, it is just number game only. We'll see only number of members only we'll see. Exactly. Colligative properties also, it depends on number of solute particles but not on their nature. Right, then total how many colligative properties are there? Let's see the list of various colligative properties. First colligative property is relative lowering of vapor pressure. Relative lowering of vapor pressure called as RLVP. Relative lowering of vapor pressure. Second one is elevation of boiling point. Elevation of boiling point, which is designated with delta TB. Third colligative property is depression in freezing point. Depression in freezing point, which is designated with the delta TF. And the last and fourth colligative property is osmotic pressure. Osmotic pressure. These four are, which is of course designated with the pi symbol. These four are the colligative properties. Now we'll say one by one all colligative properties. Let's take first relative lowering of vapor pressure. First one is relative lowering of vapor pressure, which is designated with the RLVP. That's it. Right. Then before we're going to start a relative lowering of vapor pressure, we'll see here how many definitions are combined like this. Relative lowering of vapor pressure. It includes vapor pressure as well as lowering of vapor pressure as well as relative lowering of vapor pressure. It includes total 3 definitions, remember. First, already what is vapor pressure in the last video only I explained. Once again we'll recall then what is vapor pressure. The pressure exerted by the vapor on the surface of liquid at equilibrium state is called as vapor pressure. The pressure exerted by the vapor on the surface of liquid at equilibrium is called as vapor pressure. Right. First we'll see lowering of vapor pressure. First we'll see what is the lowering of vapor pressure. After that we'll go to relative lowering of vapor pressure. Okay, we'll see what is the lowering of vapor pressure. Very simple concept. See here, it is one container. We'll take pure solvent here. Here same container, same solvent we'll use. Both are same. Here water means water, 1 liter, same, quite same. Right. Then closed container, of course, both. Now, here what happened then? It is a volatile. It is a pure solvent. Volatility will be there. Then from surface, what happened? Evaporation takes place. Evaporation takes place, and it is a closed container. Because of closed container, again condensation takes place. Condensation takes place. During the condensation process, what happened? Those vapor particles are exerting pressure on the liquid surface. That is called as vapor pressure. It is a pure solvent. That's why it is, of course, P naught. Vapor pressure of pure solvent, which is designated the P naught. P naught. Right. Come here. Same water only, same solvent only, pure solvent. In that solvent, what I am doing? Some non-volatile solute particles are added. Here some non-volatile solute, non-vaporizable solute particles are added. Automatically what happened then? Those non-volatile solute particles also occupies the surface area also. Here on surface area, pure solvent molecules are there. Here on surface area, pure solvent molecules along with that non-volatile solute particles also present. Because of that reason, what happened then? Evaporation tendency decreases. Because only few molecules are evaporated. Because these non-volatile solute particles will not evaporate. Here all molecules are evaporated. All, because it is a pure solvent, all are evaporated and all molecules are exerting pressure. But here only few are evaporating. Only pure solvent is evaporating. Non-volatile solute is not evaporating. And if it is a closed container, what happened then? Again, those particles, when they are combining, when they are come back, they will exert pressure. They will exert some pressure. Definitely, when both pressures, if we compare to each other, here vapor pressure is less. Here vapor pressure is more. Here vapor pressure is less. Why here vapor pressure is less? Because here non-volatile solute particles are added. Those non-volatile solute particles are not evaporating automatically, and at the same time they are occupying some surface area also. Automatically evaporation tendency decreases, simultaneously vapor pressure also decreases. Here this vapor pressure I am designating with a P symbol. P, it is of course a P naught. It is a P naught, it is a P solution also we can write. It is a solution because in solvent solute particles are added. Solvent and solute, nothing but a solution. Okay, that's why how to define. Now our target is lowering of vapor pressure. We have to define lowering of vapor pressure. Means here vapor pressure is lowering. Here vapor pressure is decreasing. Why vapor pressure is decreasing? Due to addition of non-volatile solute. That's why how to define lowering of vapor pressure means the decrease in the vapor pressure of solvent, the decrease in the vapor pressure of solvent due to addition of non-volatile solute is called as lowering of vapor pressure. The decrease in the vapor pressure of solvent due to addition of non-volatile solute is called as lowering of vapor pressure. Or in another manner also we can tell lowering of vapor pressure, we can also tell like this, that is P naught minus P. P naught minus P. Yeah, how to define the difference between vapor pressure of a pure solvent and vapor pressure of solution which contains non-volatile solute. I'll repeat, the difference between vapor pressure of a pure solvent and vapor pressure of solution which contains non-volatile solute is called as lowering of vapor pressure. We can also designate it with a delta P symbol. Delta P, nothing but lowering of vapor pressure. Next we will see relative lowering of vapor pressure. Relative lowering of vapor pressure definition, let's discuss now. Relative lowering of vapor pressure. Very simple. See here, already P naught minus P solution. This already known to you, it is lowering of vapor pressure. Lowering of vapor pressure by P naught I am taking. It is just ratio only. This ratio only called as a relative lowering of vapor pressure. How to define then the ratio of lowering of vapor pressure to the vapor pressure of pure solvent is called relative lowering of vapor pressure. Once again, the ratio of lowering of vapor pressure to the vapor pressure of pure solvent is called as relative lowering of vapor pressure. And this relative lowering of vapor pressure is first colligative property. This is only first colligative property. Definitely depends on number of solute particles. Why? If more solute particles are there, then the lowering of vapor pressure is more. Remember, overall relative lowering of vapor pressure is depending on definitely number of solute particles, because it is a colligative property, right? Then next in this concept one important thing we have to learn, that is a Raoult's law. So already Raoult's law we have learned or not previously? Yeah, absolutely, we have learned previously Raoult's law for volatile components. See here carefully, it is a solution, it is a mixture. Here component 1 is there and component 2 is there. Both are volatile. If both are volatile, it is volatile, it is also volatile. When both are volatile, how we have discussed, how we have explained Raoult's law, that already known to you. When both are volatile components, it's a related Raoult's law we have learned in our previous classes. Now we will discuss another type of Raoult's law. What is that? Raoult's law of a solution which contains a non-volatile solute. If both are volatile, how to explain Raoult's law already known to you. Now what we are doing, we will discuss about a solution. We will take one solution. In that solution, non-volatile solute particles are there. Means here both components are volatile. Here only one component is volatile and other component is non-volatile. One is volatile, one is non-volatile. If present, how to explain Raoult's law? Let's discuss now. Once again, here both are volatile, but here only one is volatile, one is non-volatile. That's it. In that case, how to explain Raoult's law? Let's discuss now. Okay? Right. Raoult's law here we will discuss as part and parcel of relative lowering of vapor pressure. After completion of its derivation, you will understand why we are learning Raoult's law in this concept. We will understand shortly. Okay? Now we will see Raoult's law of a solution. Raoult's law of a solution which contains non-volatile solute. Non-volatile solute. Raoult's law of a solution which contains a non-volatile solute. We'll see its derivation part. Right. Here one important thing is, now I am giving its derivation part completely according to our NCERT book. Remember, in NCERT book, how he has taken symbols, same type symbols I am using and I am explaining. I am not using a different symbols, remember. Whatever the symbols has given the NCERT book, I am following exactly as it is. Please try to understand how I am using those symbols. See here carefully. Now what we have to do, Raoult's law of a solution which contains a non-volatile solute. What we are doing first, once again we will go back to our previous Raoult's law. In previous Raoult's law, we have taken both are volatile only. That formula once again I will write here. That is P solution, nothing but P mixture, is equals to P1 plus P2. Two components are present. Two components are present. Both are volatile. How we have written now? We have written as P1 naught x1 plus P2 naught x2. We have taken. This is our previous Raoult's law. Sir, why we are using the previous Raoult's law? Based on previous Raoult's law only. Now present Raoult's law statement and its derivation will see. Okay? Right. It is a previous concept. Here both are volatile. P1 naught x1, P2 naught x2. And here just now we have discussed here non-volatile solute. Solute is non-volatile. If a solute is non-volatile, please try to understand. It is a solvent. Now it is a solute. Only solvent is vaporizing. Only solvent is exerting pressure. Solute is not vaporizing as well as the solute is not exerting any pressure. And already known to you, solvent we have designated as 1, solute is designated as 2. That's why in this formula what I am doing, wherever 2 term is there, that I am just neglecting. P2 naught x2 I am neglecting, I am taking it as 0. Why? Because it contains a non-volatile solute. Solute is non-volatile, automatically its pressure also 0. No pressure, no evaporation, no pressure. That's why it is taking as 0. Therefore, if it is 0, this P2 also taking as 0. Now what we can write? P solution. P solution is nothing but just P1 only, remember. P solution is nothing but 1. Why 1 only? Because 2 0. If 2 0, this 1 only we can take it as a solution vapor pressure. That is very, very important. I am explaining according to our NCERT book, remember. Okay, here 1 means don't consider as a solvent. Here 1 means, in this particularly, in Raoult's law, which contains non-volatile solute concept. If 1 is there, means that is a solution vapor pressure only. E is equals to, we'll write P1 naught x1. This formula now we have to use to extend or to get the final formula of Raoult's law. Therefore, P1 equal to P1 naught x1. What is P1? P1 is nothing but a solution vapor pressure. Solution vapor pressure. Right. Next, just now we have taken a lowering of vapor pressure. Lowering of vapor pressure formula delta P is equals to P1 naught minus P solution I have taken. Now, instead of solution, I will write P1. Instead of solution, I will write P1. Therefore, P1 naught minus P1 I will write. P1 naught minus P1. What is P1? P1 is nothing but a solution vapor pressure, because which contains a non-volatile solute. Right. Therefore, we'll write like this. P1 naught minus P solution here. Sorry. Right. Okay, we'll continue. That is equals to P1 naught minus what is P1? We'll write P1 equal to P1 naught x1. P1 naught x1. Just I copied as it is. Whatever the P1 is there, that P1 I have copied here. Just substituted, that is delta P is equals to. Right. We'll continue now. Delta P is equals to. So here P1 naught is there, here also P1 naught is there. I'll take P1 naught as common. P1 naught 1 minus x1 we are getting. Okay, here P1 naught is there, 1 minus x1. Then already known to you, x1 plus x2 equal to 0. Sorry, x1 plus x2 equal to 1. Because the sum of mole fractions of all the components equals to 1. From that formula, what is 1 minus x1? 1 minus x1 equals to x2. Therefore, I will substitute x2. Delta P is equals to P1 naught into x2. I am substituting. Right. Next, delta P, once again I will write. What is delta P? P1 naught minus P solution. P1 naught minus P solution. P solution nothing but P1. Therefore, instead of delta P, I will write once again P1 naught minus P1 I am taking. What is meant by P1? P1 is nothing but pressure, partial pressure of solution which contains a non-volatile solute. is equals to P1 naught X2, of course. Now P1 naught I'll bring LHS. P1 naught minus P1 by P1 naught is equals to X2. This is only Raoult's law for a solution which contains a non-volatile solute. See here, P1 naught minus P1 by P1 naught, it is nothing but a relative lowering of vapor pressure. It is a relative lowering of vapor pressure, one of the colligative property, is equals to mole fraction of solute. Mole fraction of solute. Based on this formula, we have to define what is Raoult's law. What is Raoult's law? The relative lowering of vapor pressure which contains or the relative lowering of vapor pressure of solution which contains non-volatile solute is equals to mole fraction of solute in the solution. I'll repeat. The relative lowering of vapor pressure of a solution which contained non-volatile solute is equals to mole fraction of solute in the solution. That's it. This is about Raoult's law of a solution which contains a non-volatile solute. Because in our NCERT book, same formula he has given. P1 he has mentioned. P1 means don't confuse, it is not a solvent. It is a solution which contains a non-volatile solute. Right. Okay. Next, we'll just extend this formula. How to extend the formula? Let's discuss now. Here, mole fraction of solute. What is mole fraction of solute? Number of moles of solute by total number of moles. Therefore, P1 naught minus P1 divided by P1 naught is equals to X2 equal to N2 divided by N1 plus N2 is also formula, Raoult's law formula. Now again I am extending, while extending for very diluted solutions, remember, for very diluted solutions, solute as well as solvent quantities, if you observe, solute quantity is negligible. Solute is very minute comparing with the solvent. For very diluted solutions, solute is very less comparing with the solvent. Based on that, what I am doing, here N2 solute moles, N1 solvent moles. Then for diluted solutions, N1 value is very greater than, very more than N2. Number of moles of solvent is more than solute. That's why in the denominator, solute moles I am neglecting in the denominator. Therefore, P1 naught minus P1 divided by P1 naught is equals to, we'll write N2 by N1, that's it. Why? Because N2 moles are very less for diluted solutions in the denominator. So solute moles I am neglecting. Therefore, you will get N2 by N1. This formula also again we can extend. How to extend means, see here, I'll write here remaining things. Last final formula, that is P1 naught minus P1 by P1 naught is equals to, what is N2? Number of moles of solute. Formula mass by molar mass. We'll write like this, W2 by M2 divided by N1, W1 by M1. Then we'll shift P1 naught minus P1 divided by P1 naught is equals to W2 by M2 into M1 divided by W1 is our final Raoult's law formula. Now we'll see the terms one by one. Terms, let's discuss now. What are the terms? P1 naught, vapor pressure of pure solvent. Always remember, if not 0 is there, means it is definitely pure substance only, pure substance vapor pressure. One symbol, solvent, right. Next, P1 is very important. P1 is nothing but vapor pressure of a solution which contains non-volatile solute. non-volatile solute. Then what is W2? 2 for solute, mass of solute, and M2, molar mass of solute, and as well W2 or W1 now. 1 is for solvent, mass of solvent, M1, molar mass of solvent. That's it. These are the terms. Based on this formula only we will have some problems. We have to solve problems, which is very important for both theory as well as competitive examinations purpose. Okay, this is about Raoult's law. Now I will give you once again just briefly the entire solution, entire derivation part. Raoult's law. Okay, before we will going to discuss Raoult's law of solution which contains non-volatile solute, we will go back to Raoult's law of a solution which contains volatile components. Both are volatile. If both are volatile, how to write? P solution is equals to P1 plus P2 is equals to P1 naught x1 plus P2 naught x2. This already known to you. Now we are discussing for non-volatile solute. Non-volatile solute means a solute partial pressure is 0, we can neglect. Therefore now P solution is nothing but a P1 only is equals to P1 naught x1. Now it is a solution vapor pressure which contains non-volatile solute. Now we will go to lowering of vapor pressure. Delta P is equals to P1 naught minus P solution. Now instead of solution I will write P1. Therefore P1 naught minus P1. Therefore delta P is equals to P1 naught minus P1. What is P1? P1 is nothing but P1 naught x1. This I am substituting here. And P1 naught, if you take common 1 minus x1, and P1 naught x2, delta P is equals to, once again we will write P1 naught minus P1, delta P equal to, it is P1 is nothing but a solution pressure, it is equal to P1 naught x2 will shift left side. Therefore P1 naught minus P1 by P1 naught we are bringing here is equals to x2. This is only Raoult's law of a solution which contains a non-volatile solute. How to define now? The relative lowering of vapor pressure of a solution which contains non-volatile solute is equals to mole fraction of solute in the solution. That's it. And how to extend this formula just now I explained. Okay, right. Now based on this Raoult's law we'll solve some questions, some problems we'll solve now. Okay. Yeah, we'll continue the question. First we'll understand the question. The vapor pressure of a pure benzene at certain temperature is 0.850 bar. Means here pure benzene vapor pressure given, there is nothing but P naught given. Next, a non-volatile non-electrolyte solid solute, of course its weighing 0.5 grams means W2 has given, weight of solute has given, when added to 39 grams of benzene, weight of a solvent also given, as well as solvent molar mass also given, and vapor pressure of a solution also given. Pure solvent P naught is there, P1 nothing but a P solution is also given. What is the molar mass of a solid substance? Nothing but M2 is asking. First we will write given information, data will write P naught is equals to 0.850 bar. Next this one P1 or P solution will write, because 1 means again we will get confusion, that's why P solution is equals to 0.845 bar. Okay, next non-volatile solute, that is a W2 is equals to 0.5 grams, and M2 is asking a question mark. Next W1 mass of solvent 39 grams, and M1 molar mass of solvent benzene 78, and this is the data. Now we'll write the formula, come on. P naught minus P by P naught. Here P better P1 or P solution, any symbol we can write, but generally if you write 1 always in the exam or anywhere, there is no any wrong, but if you write 1 means suddenly we will get somewhat confusion. That's why P solution better will write. Okay, P solution will write is equals to W2 by M2 into M1 divided by W1. Now we'll substitute P naught 0.850 minus 0.845 divided by 0.850 is equals to W2 0.5 by M2 only we are calculating M1 78 divided by 39, just substituted the data, and if you do the calculation, it is a subtraction, you will get 0.005 divided by 0.850 is equals to 39 2s 0.5 into 2 1 by M2, and if you simplify you will get molar mass of solute 170, you will get 170 units gram per mole is your answer. That's it. What is M2? 2 for solute, M for molar mass. Molar mass of solute is 170 gram per mole. This question asked n number of times in the annual examination, remember. Very, very important question and a very simple question also. Everything is given, everything, all the values given, just we have to calculate molar mass of solute. That's it. Our formula P naught minus P solution. P solution by P naught. It is the vapor pressure of pure solvent P nothing but P solution, or P1 nothing but the vapor pressure of a solution which contains a non-volatile solute. Right. Next question we'll see then. Yeah, next question is like this. Calculate relative lowering of vapor pressure when 5.85 grams of common salt, nothing but sodium chloride, is added to 100 milliliters of water. Here directly asking a relative lowering of vapor pressure, nothing but a P naught minus a P solution by P naught only asking. We will write the given data. What will write means question is relative lowering of vapor pressure, otherwise we will write a P naught minus P solution by P naught. P naught 1 of course is equals to question mark, that only asking. Next is asking, he has given 5.8 grams of common salt, mass of solute has given 5.85. And next we'll do one thing. Here 5.85 grams is considerable amount, remember, considerable amount, that's why solute mass also will consider in this question. That's why we have to use this formula here. What formula you have to use? That is a P1 naught minus P solution by P1 naught is equals to, instead of mass we will use directly moles related formula. Mole fraction, that is x2 is nothing but n2 divided by n1 plus n2 is our suitable formula here. Here solute moles also will consider because n2 also will consider in the denominator, because considerable amount has given in the question, remember, should not neglect here. That's what is our job now. Solute moles, solvent moles we are calculating. Okay. Here mass of solute 5.85 and molar it is a solute, mass of solute symbol is W222. Solute 5.85, molar mass of solute NaCl common salt is nothing but sodium chloride. Sodium is 23, 35.5, 58.5. Immediately we will find N2 molar mass of solute. That is mass by molar mass. W2 by M2 is equals to 5.85 divided by 58.5. If you do, then you will get 0.1 of course is obtained. Okay. Next what we are doing, same N1 also we are calculating now. N1 purpose W1 by M1. We'll write first what is W1 and what is M1. W1 mass of solvent, but unfortunately here mass of solvent has not given. Instead of mass, volume has given, and that is water. If a volume given, nothing but mass given indirectly, because density of water is 1 gram per milliliter. That's why whatever the volume is there, same will write as mass, because volume into density you will get mass. That's why mass will write directly 100 grams. How you will get mass? Mass is equals to density into volume. Density into volume. 1 into 100, nothing but 100. Based on this we have written. And molar mass of solvent is 18. Therefore now N1 W1 by M1, nothing but 100 divided by 18, 5.55 something. Now these values if you substitute here, P1 naught minus P solution by P1 naught is equals to N2 is 0.1 divided by 0.1 plus 5.55. If you simplify, finally you will get 0.018. 0.018 is obtained. That is a relative lowering of vapor pressure. That's it. Okay. Here a volume of solvent has given. That volume I have converted into mass with the help of this formula. Therefore, mass by molar mass 100 by 18 and nearly 5.55 you will get. That if you substitute there, you will get 0.018. Here P naught minus P by P naught equal to W2 by M2 into M1 by W1 formula we should not take. Why? Because solute is also considerable amount is there. That's why the entire formula we have to take here. Right. Next question. Yeah, this question will try to understand. 1 gram of non-volatile solute was dissolved in 100 grams of acetone, whose molar mass is 58 at 298 kelvins. The vapor pressure of solution was found to be 192.5 millimeters of mercury. Calculate molar mass of solute. Again molar mass of solute M2 asking. Vapor pressure of pure acetone, nothing but pure solvent, is 195. We'll do one thing. I'll give you its complete data. Calculation is your job. I already given its answer also. See here data we'll see now. Vapor pressure of pure word is there, nothing but P naught. P01, vapor pressure of pure solvent. Okay, solvent, pure acetone at 298 Kelvin is 195 millimeters of mercury. Next, P solution is equals to this one. Because the vapor pressure of solution as mentioned 192.5 millimeters of mercury. 1 gram of non-volatile solute W2, 1 gram non-volatile solute was dissolved in 100 grams of acetone. Acetone is solvent. That is nothing but W1 is 100 grams. Next, here W2 is there. M2 is question mark. That only we are calculating. Calculate molar mass of solute. And one more value is required. That is M1, molar mass of solvent. Who is solvent here? Acetone is solvent and already its molar mass given 58. Our formula already known to you. P01 minus P solution by P01 is equals to W2 by M2 into M1 divided by W1 is our formula. Please substitute all the values carefully and calculate you just substitute and calculate it. You will get this much answer. Which one? M2 equal to 45.3 gram per mole. Always molar mass unit is gram per mole only. Okay, right. We'll see next problem then. Okay, next question is like this. A 16% by mass, W by W, mass percentage, solution of sulfur in carbon disulfide has a vapor pressure 50 millimeters of mercury. Means it is a solution vapor pressure. Solution vapor pressure. And what is the vapor pressure of a pure CS2? Pure solvent vapor pressure he is asking. Nothing but a P1 naught he is asking. Pure solvent vapor pressure he is asking. Right, how to solve this question? Let's discuss now. We'll first write its meaning. 16% by mass, W by W. Meaning is 16% W by W means 16 grams of solute. Who is solute? Sulfur. Sulfur. In solvent is CS2, 100 grams. Both are grams only because it is a W by W. Solute is W, solvent, solute is W, solution also W only. Solute is W, solution also W only. Right. See here, twist. 16 grams of sulfur present in 100 grams of solution, not solvent. According to percentage W by W, we have to recall it is a mass of solute, it is a mass of solution, not solvent. Of course, it is a solute, and it is a solvent, doesn't matter. But first we will write the information, correct information. 16 grams of solute is present in 100 grams of solution, right. Now, solute mass is there, solution mass is there. From this, we can calculate a solvent mass. Whose mass? CS2 mass. Solvent mass also we can calculate. Therefore we'll write like this. Solvent, mass of solvent. There is nothing but W1, mass of solvent is W1 is equals to solution is 100 minus solute is 16. 100 minus 16 if you do, you will get 84 grams is the mass of solvent. Okay, means 16 grams of sulfur is present in 100 grams of solution, or 16 grams of sulfur is present in 84 grams of CS2. Any one we can tell. Both are correct only. Okay. Then M1, mass of solvent, molar mass of solvent. That is, who is solvent? CS2. CS2 molar mass. Carbon disulfide molar mass, we just calculate, it is a 76 you will get. Okay. Then from this we will find a mole, number of moles of solvent. W1 divided by M1, 84 divided by 76. 84 divided by 76, you will get 1.11. Next, W2, mass of solvent 16 grams. And M2, molar mass of solute, mass of solute 16 grams. Molar mass of solute. Who is solute now? Definitely sulfur is solute. Molar mass of sulfur, already familiar, that is a 32. Therefore N2 is equals to W2 divided by M2. That is a 16 divided by 32. Of course 1 by 2, 0.5 we can write. N2 value 0.5. Now we'll find a mole fraction of solute. Mole fraction of solute will calculate. That is mole fraction of solute. Solute is nothing but 2. What is the formula? N2 divided by N1 plus N2. N2 divided by N1 plus N2. N2 is 0.5 divided by N1 is 1.11 plus 0.5. If you simplify, mole fraction is 0.31, you will get 0.31. But our answer is not a mole fraction of solute. Our target is vapor pressure of pure solvent, nothing but. We will write a remaining dot also. Here, P1 naught, question mark. and P solution, vapor pressure of solution has vapor pressure of solution 50 millimeters, 50 mm of Hg. Right, we'll take again our Raoult's law formula. I'll just remove here. I'll write here formula. There is a P1 naught minus P solution divided by P1 naught is equals to N2 divided by N1 plus N2, nothing but X2. Already X2 we have substituted. That's it. Then I will just substitute the values. P1 naught only our target, minus P solution is 50 divided by again P1 naught. Sorry, right here P1 naught, right, is equals to mole fraction is 0.31. Next we are doing a cross multiplication here. Cross multiplication will do P1 naught minus 50 is equals to 0.31 P1 naught, 0.31 P1 naught, okay, 0.31 P1 naught, and if you do simplification you will get 72.46. P1 naught value 72.46 millimeters of mercury. Remaining simplification you have to do then. This is about calculation of pure solvent vapor pressure. Pure solvent vapor pressure we have calculated. Okay. Next, we'll go to next question. Yeah, okay. Okay, of course, maximum questions has covered. Directly we'll start a second colligative property, that is elevation in boiling point. Elevation boiling point, second colligative property. Elevation in boiling point or elevation of boiling point, doesn't matter. Elevation of boiling point. Will indicate with the delta TB symbol. Right. Let's see now what is meant by elevation of boiling point. Name itself indicating elevation. Elevation is nothing but increasing of boiling point. Why boiling point increases, everything we will discuss, but before that we have to know what is meant by boiling point. What is meant by boiling point means, once again we will go back to vapor pressure concept. What is vapor pressure means? It is a solvent. Then what happened? Evaporation takes place, then condensation takes place. During the condensation, what happened? Then vapor molecules are exerting pressure on the liquid surface, is called as vapor pressure, already known to you. Now what is meant by boiling point? See the definition carefully. At what temperature, at which temperature vapor pressure equals to atmospheric pressure. Atmospheric pressure means 1 atmosphere. At which temperature vapor pressure becomes equals to atmospheric pressure, that temperature only called as boiling point of that liquid, remember. Once again, at what temperature vapor pressure of that liquid becomes equals to atmospheric pressure, then that temperature is called as boiling point. It's boiling point. As far as water is concerned, remember, as far as water is concerned, at 100 degrees centigrade, vapor pressure of water becomes equals to atmospheric pressure. As far as water is concerned, at 100 degrees temperature, vapor pressure is equals to atmospheric pressure. That's why 100 degrees centigrade is called as its boiling point. That's why at what temperature, okay, now vapor pressure becomes equals to atmospheric pressure, then that temperature is called as its boiling point. Right. Now what is meant by elevation in boiling point? Let's discuss now. Elevation, nothing but increase. See here carefully. It is pure water again. Pure water, say its boiling point is 100 degrees centigrade. Pure water boiling point is 100, means at 100 degrees centigrade its vapor pressure becomes equals to atmospheric pressure. Next what I am doing, in that water some non-volatile solute particles are added. Some non-volatile solute particles are added. Then if non-volatile solute particles if I added, then I want to make its vapor pressure becomes equals to atmospheric pressure. Once again, it is a pure solvent. At 100 degrees centigrade, vapor pressure becomes equals to atmospheric pressure. But here some non-volatile solute is there. When non-volatile solute is there, same at 100 degrees centigrade, its vapor pressure is not equal to its atmospheric pressure. Still more heat we have to do. Means instead of 100, I am giving general symbol, instead of 100, say at 120, suppose at 120 degrees centigrade, its vapor pressure becomes equals to atmospheric pressure. Because of presence of non-volatile solute, more heat we have to do. More heat we have to do, then only its vapor pressure becomes equals to atmospheric pressure. When you are comparing to each other, definitely boiling point of solution is always higher than boiling point of pure solvent. Why boiling point of solution is higher? Because of presence of non-volatile solute. Okay, now due to presence of non-volatile solute, then at 100 degrees centigrade, it is not, at 100 degrees centigrade, its vapor pressure is not equal to atmospheric pressure. Still more heat we have to do. Then suppose it may reach at 120 or 130 something. Then at this temperature, its vapor pressure becomes equals to atmospheric pressure. Therefore, definitely pure solvent and a solution, when you are comparing to each other, solution boiling point is always higher than pure solvent due to presence of non-volatile solute. Therefore, we will write that only here delta TB is equals to, here I will write TB minus TB naught. We will see the symbol. What is the TB? TB is nothing but a vapor pressure of solution. TB naught, vapor pressure of naught, zero, not indicating a pure solvent. Vapor pressure of pure solvent. Okay, always TB is higher. TB naught is lower. It is a solution vapor pressure. It is a pure solvent vapor pressure. This is only called as elevation in boiling point. Now, how to define elevation in boiling point means the difference between boiling point of solution and boiling point of solvent. I'll repeat. The difference between boiling point of solution which contain non-volatile solute to the boiling point of pure solvent is called as elevation in the boiling point. This is our definition. Okay, right. Next we can write like this. That is, experimentally, remember, experimentally we will get one relation. Experimentally, elevation in the boiling point. Experimentally, elevation in the boiling point always directly proportional to molality. Experimentally, elevation in boiling point is directly proportional to its molality. Experimental result it is. Now I will remove this proportional symbol. Delta TB is equals to KB into M. We are getting a new symbol, that is KB is a new symbol. What is delta TB? Elevation in the boiling point. What is M? Molality. What is KB? KB is nothing but molal elevation constant. Molal elevation constant, or its another name is molal ebullioscopic constant. Molal ebullioscopic constant. Which one? KB. Now I want to define KB. KB, how to define? KB is equals to delta TB divided by M is the formula. How to define KB? For that purpose I am doing if M equal to 1, then KB equal to delta TB. Based on this, how to define Kb, how to define molar elevation constant means very simple. Very simple. Elevation, Kb is also elevation boiling point only. Okay, na? Molar elevation is constant is also elevation boiling point at or when 1 mole of solute is present in 1 kg of solvent. Once again, Kb is also elevation only. That's why then elevation boiling point occurs. Elevation boiling point when 1 mole solute present in 1 kg solvent. Because molality we are taking 1. Molality taking 1 means what is the meaning? 1 mole solute is present in 1 kg. Then only molality equal to 1. That's why Kb is also delta Tb when m equal to 1. Means molar elevation constant is also elevation boiling point only. But when means when 1 mole solute is present in 1 kg solvent. Now we will write its units also. Units. What are the units? Delta Tb, difference Kelvin, molality, mole per kg. Therefore it is a 1 by kg. That's why we will get its units. Units are Kelvin, kg will come here, kg per mole. Kelvin kg per mole is the unit of molar elevation constant. Right. This is about elevation boiling point. Still elevation boiling point graphical study is there. Graphical study still we did not discuss, and in this molar elevation boiling point, one more its extension formula is also there that we'll discuss. But before that, once again we will see elevation boiling point. How to define means the difference between boiling point of a solution which contained non-volatile solute to the boiling point of pure solvent is called as is called as elevation boiling point. Experimentally, elevation boiling point is directly proportional to molality. Therefore, if you remove the symbol, you will write Kb. What is Kb? Molar elevation constant or molar bilioscopic constant. How to define molar bilioscopic constant? Means molar bilioscopic constant is also elevation boiling point only, but when means when 1 mole solute is present or 1 mole solute is present in 1 kg of solvent. Okay, right? Then it's a graphical representation as well as its remaining things will continue in our next class. Okay, thank you for watching. Bye.